Hello and welcome to another power electronics class. In the previous class, we spoke a little bit about different losses in power electronics and also different type of switches, different type of semiconductors such as thyristors, diodes, um, and different type of transistors. We learned that we have three different types of switching tools. We have uncontrollable, which are diodes. We have half controllable, which are thyristors, and we have controllables. And we went a little into the details of semiconductors and how the p-n junction works. Uh, we discussed a little bit about the loss in the system and how an ideal semiconductor performs, and in real world how the thyristors and diodes and transistors operate and the different losses that they have. Today we will continue with the losses, and we will solve some problems, practice problems as well. So for the switching losses, this is an example of a switch. We have different type of delays. We have the TD on, which is the turn on delay, the time that it takes for the diode to turn on or the transistor to turn on. We have the TD off delay or turn off delay. We have the current rise time, which we show it with TRI. We have the voltage fall time, which we call it TVF. We have the voltage rise time, which is TRV, the current fall time, which is TFI, and the crossover time. And as mentioned in the previous class as well, most of the loss in a switch occurs in the switching time. Obviously, we have leakage current and forward voltage, forward bias voltage, which is a drop in the voltage when we turn on the switch. But the majority of loss, and as you can see here, is during the switching itself. So when you turn off a switch, what happens is for the p-n junction, usually if it's a diode, to get saturated again, it takes a little bit of time. Let me go back and show you the p-n junction one more time. So for the p-n junction to become saturated, meaning all of these become negative and all of these become, all of these become positive and all of that becoming negative, it takes a little bit of time for all the p-n junctions to become saturated. And that is actually equal to the rise time that we have here. Again, if we have a diode, if it's in forward bias, if we have an ideal diode, then the voltage of forward bias for an ideal diode is around 0 volts. Non-ideal diode like a silicon diode is 0.7. So you can see that the voltage turned off because it's an open circuit. Ideally, it's an open circuit. VD would be equal to Vmax. And when it's switched and turned on, it drops to 0, almost 0. In real world, you have a V on, which is for silicon, for example, silicon diode, this is 0.7 volts. What happens to the current when we go from on to off? So when we are turned on, the current, I'm going to call it I of F, is equal to 0. Or is it equal to the max? 0 or max. When this is short circuit, what is the current passing through this? maximum. Thank you. And when it's open, I of open circuit, what is I equal to? 0, because we don't have any connection between them. The impedance is infinite. So what happens is when we are going from off to on, the current goes from 0 to its maximum current, which here is I out. And this is when it's in the on situation. This is when it's in off. So this part is in off. And so it takes some time from the current, for the current to go from 0 to its maximum, and it takes some time for the voltage to go from maximum to its 0. And in between these two, let me erase these. Do you remember what power is? The equation for power, general equation for power. VI. Yes. So here we have voltage and we have some current, and therefore this would be my total loss, the power loss, PVI. And you can see here that in these two areas, when the switch is turning on and off, I have the maximum power. Which is being wasted. This is wasted power. So here we have the VC on, and here we have the PC on, or W if we want to find the total energy loss, and WC off. And the rest of the time, if we have an ideal which V on is 0, but technically it's not 0, the power loss is much less compared to when you are switching it on and off. So the power loss would be right around here when it's turned on. And also when it's turned off, you have a little bit of leakage current, so it's going to be a little bit of power loss. But the majority of power loss happens when you're going from on to off or off to on. So again, to summarize it, if we have a switch, here it's a thyristor or a diode or whatever, and we are going from off to on, back to on. So off, on, off, and back to on. So when we are in the off situation, means the switch is, if it's an ideal switch, it's an open circuit, and the current is at its minimum, and the voltage is at its maximum. And this is when we are off. And we are on, it looks like it's short circuit if it's an ideal switch, meaning the current is maximum and the voltage is at its minimum. Why? Because we have V positive minus V negative gives us V output, and here it's almost equal to 0 if we have an ideal switch. For an ideal switch, we would immediately go from off to on, back to off. But since we have a semiconductor and it takes time for the p-n junction to become saturated, for the electrons to move and for the holes to move, then we would have a rise time for the current. So the current rises, and we have a fall time for the voltage. And in between these two, we have a loss. So again, it doesn't go immediately from off to on or on to off. And it's the same thing when we go from on to off as well. So here again, we have on to off. We have a little bit of delay, and it takes some time for the current to drop and for the voltage to rise as well. In between these two, we have a leakage current when it's turned off, and we have a forward or V on voltage when it's turned on. So we still technically have a little bit of loss, but compared to the switching loss, the moment that it switches, that's relatively low. Now, the equation to measure these two losses in these turning on and turning off switch, we can just find the area under the graph or the curve, and this would be our loss. And again, the majority of the losses is caused by switching itself. If the switching frequency Fs is 1 over Ts, the effects are linear. So Ps would be half of Vd I out Fs Tc on plus Tc off. So what was Tc on? What is Tc off? It's the switching on time and the crossover between on and off. The turn on and off times must be short in order to use a high frequency or Fs. And a on state, the power loss would be P on would be V on, I on, T on over Ts, and P on would be dRds on I out squared. I want you to write these equations, write down these equations. We're going to have a short quiz from these two problems. Just give me a second. Give you a few pairs. Again, this is just for attendance mainly. Problems are going to be pretty simple. They're just replacing the numbers. Okay, did you write it down? A minute to write down. So again, the energy loss that we have here, the power loss, is going to be half of Vd IOFS Tc on plus Tc off. Now for the first problem, if Vd is 200 volts, I out is 10 amps, the frequency is 20 kilohertz, and Tc on plus Tc off is going to be 200 nanoseconds. We want to calculate the switching loss Ps. I'll give you 5 minutes. Oh, there are two other problems. Yes. Okay. What did he get? Perfect. Yes. So PS is equal to half VD IO FS TC on plus TC off. I'm gonna write it here. So it's gonna be half. What is VD? It's 200. What is IO? 10 amps. FS is 20 kilohertz or 20,000, thank you, hertz. And TC on plus TC off is 200, but it's in nanoseconds, so times 10 in the power of negative 9. Multiply all of them, we get 4 watts. Okay. Second problem, if V on is 2 volts, I out is 5 amps, T on is 5 milliseconds, and TS is 20 milliseconds. We want to calculate the on-state power loss. Give you again 5 minutes. Did you all get the answer? What is it? So V on would be equal to 2 volts. IO, it's 5 amps. I don't need to write it again. So P on is equal to V on, I naught T on over TS. V on is 2 volts. I is 5 amps. And T on is 5. And TS is 20. Both of them are in milliseconds, so it doesn't matter actually. So it's going to be 10 times 0.25 gives us 2.5 watts. Yes. Now the third problem, what happens to switching losses if the switching frequency is doubled? Give you a few minutes to think on it. Okay. So as mentioned before, there is a linear relationship between the power loss and the frequency. So we have a linear relationship between power loss and frequency. Therefore, if the frequency doubles, the power loss also doubles. So doubling the switching frequency doubles the switching loss. So the question is, it doubles. Now, why do we have this? Obviously, if you have more switching in a certain period of time, if you have one switch, you're going to have one power loss. If you have two switches in the same period, you're going to have double that. If you make it four times, it's going to be quadrupled that. So doubling that doubles the power loss. Now, when you want to pick a transistor such as an IGBT, usually you are given a data sheet for that transistor or thyristor or diode. And here I put an example of an IGBT, and the different values and different characteristics of an IGBT. And you can find that for any other transistor like a MOSFET or BJT and so on. One thing that you see in all these transistors is finding the collector emitter voltage. And usually we do that at a 25 degrees Celsius. Why do we do that at 25 degrees Celsius? The manufacturer provides that at 25 degrees Celsius because, as you know, for semiconductors, if the temperature changes, then the internal resistance changes, and therefore the collector emitter voltage, all the voltages and currents will also change. So at 25 degrees Celsius, the collector emitter voltage is 1700. And as you can see, by increasing the temperature going to 100, the DC collector goes to 2400. The repetitive peak collector current is 4.8 K or 4800 amps. The total power dissipation is 16 kilowatts, pretty high. The gate emitter peak voltage is negative positive 20 volts. And collector emitter saturation voltage, it's different from the collector emitter voltage. This is technically the reverse voltage that you have. The typical is 1.9. In different temperatures, you can see for 25 degrees, 125 degrees, and 150 degrees Celsius. Goes from 1.9 to 2.3 and 2.4. The gate threshold voltage is the minimum is 5.2 and the maximum is 6.4. Typical is 5.8. The gate charge is 25 microcoulombs, and the internal gate resistance is 0.65 ohms, so pretty low as well. Again, these are at 25 degrees, obviously changing them. So you can see that you can build a switch that is around 16 kilowatts. So for most inverters, this would work very easily. And the frequency that this works is pretty high as well, the IGBT. So this would easily work if you want to build an inverter like a DC to AC inverter. This works perfectly. And here, these are the internal components of a gate driver integrated circuit with a built-in fault protection system. We have the IGBT, we have the diode, the voltage source for the gate and for the op-amp that we have that controls that the transistor. This is just for you to know. It's not going to be on the exam or anything. So now we want to go through some practical considerations in designing switching power poles. The design considerations that we have are, first is the switching frequency. Again, doubling the switching frequency, we learned it doubles the power loss, so it has a linear relationship to power loss. Selection of transistors and diodes, depending on the cost. Again, some transistors are very expensive. The power that we need, output power, frequency is very important. Voltage, current, which transistor or diode we should, or thyristor we should select. The magnetic components, and also the capacitor selection. Again, we need a capacitor to smooth out the signal to create a low pass filter. But if the capacitor is too large, it's going to cause some problems. If it's too small, you can't smooth out the signal. And I'll explain how we select the capacitors as well. So to select the power transistor, power diode or thyristors, we have to look at different characteristics. First is the voltage rating. What is the output voltage that we want to get to? For example, if we want to build a inverter, a DC to AC inverter, it's a 12 volt DC input, and the output is a normal outlet, 120 volts. The voltage rating is not that high. But if we want to build an HVDC, high voltage DC system, the voltage is several thousand volts, then you need a very sophisticated system. And then we have the current rating, the same, how much power we want in the output. We have the switching speed, frequency, and the on-state voltage drop, which determines the amount of loss as well. So for ideal switch analysis, the properties of an ideal switch, the forward and reverse voltage are infinite, and the leakage current is 0. Therefore, we won't have any loss when it's turned on or turned off. It conducts arbitrarily large currents with 0 voltage drop. Again, the forward connection or the on part, you have 0 loss because we have 0 voltage drop. The forward voltage bias, again, it's 0. The instantaneous switching or turn on and turn off time is equal to 0. So it immediately goes from on to off and off to on. And the power from the gate circuitry is 0 because the resistance in the gate or the base is infinite. So we would have 0 power loss in the gate. New devices are approaching these characteristics, but obviously we don't have an ideal switch yet. Now, this graph is a very interesting graph, and it shows a comparison between different power transistors and switching devices. We have the IGCT, IGBT, MOSFET, GTOs, and thyristors, and so on. I don't know if you can see this, but if we have the X, Y, Z, this is the current. This shows the frequency, and Y shows, so imagine this is Y, X, and this is Z axis. The Y axis shows us the voltage, the X axis shows us the current, and the Z axis shows us the frequency, for example. So let me, so for example, the thyristor has a very good high voltage, 5 kilovolts, very high current, around 3 kiloamps, but the frequency that it operates is limited. So the maximum frequency that it operates is less than 1 kilohertz, around a few hundred hertz. So you can see here, the first one, this is 1 kilohertz, so it's less than 1 kilohertz. For the GTOs, you have a high frequency, but lower voltage and current rating. BJTs, you have a higher current then MCTs, lower voltage and lower frequency, and so on. So, for example, a MOSFET has the highest frequency. You can see that the frequency is around 1 megahertz. But the current, you can see that it's less than 500 amps, like around 100 amps. And the voltage as well is less than 1 kilovolts. So the voltage is less than 1 kilovolts. And the amp current is less than 300 amps, actually. But the frequency is around 1 megahertz. So, question, which of the following has the highest frequency? The IGBTs, MCTs, GTO. So first I want you to tell me which one has the highest frequency and which one has the highest voltage. I'm gonna write the voltage with V. Highest voltage rating. So which of these three has the highest frequency rating and which one has the highest voltage rating? Thank you. The IGBT has the highest frequency rating. Which one has the highest voltage rating? Because you can see that the IGBT is around here for frequency. Yes, and the GTOs have the highest voltage rating. Because you can see that the voltage is 3 kilovolts and for them maximum is 2 kilovolts. So the higher frequency Z-axis is for IGBTs, this is for further than all of them. And highest voltage is GTOs. So if you want to build an inverter for a grid which has relatively low frequency, around 60 hertz, but you need very high voltages and currents, thyristors is the way to go, or GTOs. But if you want to build a inverter for a communication system, transmitting FM, AM, or creating a sine wave, and I'll explain how you do that, and you need very high frequencies, but you need relatively low voltage and currents, the MOSFET is the way to go. So the other thing that we have is thermal design. Again, a lot of these, because of the switching losses, and we saw that it was for a 20 volts or 40 volt system is around 4 watts or something like that. So imagine what a 2 kilovolt system, how much heat that is going to generate. So it's going to generate a lot of heat. This is an example that shows a transistor, a chip with its casing, the isolation pad, and the heat sink. And the thermal dissipation of each part is shown with TJ, TC, TS, and TA. And the dissipation power that we have is basically because this acts like a heater, and all the lost power is dissipated as heat. So TJ here would be TA plus R theta JC plus R theta CS plus R theta SA, which are the internal resistance that we have in the system. Now, this shows the design trade-off between the size and the frequency. So for lower frequency, the bigger size, we have magnetics and capacitors. Again, when you build a large capacitor, the size is bigger, but it works in lower frequency. It doesn't perform in higher frequencies well. In higher frequency, it's going to be just short-circuited. And for the heatsink, it's opposite. When you have a smaller size heatsink, it works better for lower frequencies, and bigger size works better for the higher frequencies systems. So size of magnetic components and heat sinks are as a function of switching frequency is shown here. And again, one good example is the capacitor, as I mentioned. Larger the capacitor is, you have a large capacitor and it functions better in lower frequency, but it doesn't work well in high frequency. It's just gonna just drop. And it's the same thing for magnetic components as well. And the final part, so this is just for you to know. And the final slide that we have is a summary of today's class. We learned about the design of a switching power pole. We learned about the power semiconductor devices such as the diodes and thyristors and transistors. The losses in switching power poles, the switching losses and conduction losses. Next class, we will start with buck and boost converters, and also after that, different type of inverters as well. That's it for today's class. Thank you so much, and I would see you on Wednesday.